Hi guys, so in this video I will be talking about how to solve recursive questions like these by using the method of tree recursions. Okay, so let's get started. The first thing that we have to do over here is I like to create some type of columns which basically helps me to do these types of questions using pre-recursive method in a very organized and an easy way to understand manner. The way how I'll do this is the first column I usually write is iterations. Then, whoops, let me just make a good column line. Whoop. Yeah, there we go. So I like to do iterations, and then after that, I like to do t of n, which is basically my function. Then I like to write my tree. Then I like to do number of nodes. And then last, I like to write row sum. Okay, so I'm going to be going over the method. I won't be explaining how tree recursions are basically happening and how you can, by using the method of tree recursion, you're actually going to get a proper big O notation answer. I will be only focusing on how to do it or how to implement it. So the way how we start this is we first of all write the first iteration. So in this case, my first iteration is going to be I equals to 0. My function t of n is still going to be t of n over here for my first iteration. And my tree is going to start with this green highlighted polynomial function. So in this case, this would be 4n. And the number of nodes, as you can see, is just 1 in this tree. And the row sum, which is basically the sum of all the nodes that I have in my current level, is just going to be 4n. Or I will just write this in black. That's going to confuse you. Okay. Next, we have the next iteration, which is going to be I equals to 1. And the tree would then diverge, or it would divide into two branches. And this is basically signified by the value written before the recursive function. So before t n by 2, this 2 signifies how many branches will I have. So I will have 2 branches because of this 2. And my t of n is now going to be divided into 2 parts. So we are going to write t n by 2. Again, this is highlighted by the polynomial or by whatever function is written inside the t bracket. And each node in this current level is going to be defined as 4, which is your polynomial overwritten over here, times your divisor. So this is going to be n by 2, and you're going to multiply these two values, and you're going to get 2n. So each node in this current level is going to be of 2n and 2n. And my node in this current level is going to be, the number of nodes that I have in this level is going to be 2. And the row sum for this level is going to be 4n, because 2n plus 2n is going to give me 4n. Let's try to do this for another iteration. So for I equals to t n by 4, let's try to see what this gives us. So each node is going to have 2 branches because of this 2. And the answer for each node in this level is going to be 4 times n by 4, which is just going to be n. So this is going to be n, 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 and n. And the number of nodes is going to be 4. Now, there's a strange pattern that I can observe over here. For the number of nodes, when I have I equals to 0, I will always have 1 node. That is where I'm going to start. So this is going to be 2 to the power I. this works out. If I have my function 2 to the power I, where I over here is 0, it will always give me 1. So this checks out. This is like a test pattern that I think I am observing when I'm solving this question. For this one, this is 2 to the power 1. This also checks out. And for this is 2 to the power 2. This also checks out. Okay, let's try to see another case. Let's say if I had a function, for example, 3t n by 2 plus 4n. What would be the behavior that I would be seeing over there? In this case, wait, let me just take this. So we are just going to pause this for a moment because there's a general formula that we can figure out for this number of nodes. So for this is going to be 4n. This 3 highlights how many branches there are going to be. So for the first iteration, there are going to be 3 branches. So you're going to get some answers based on that. So 1, 3. And for this, you're going to get 3 more. So 3 plus 6 plus 9. That's going to be 9. And over here, we can also see that this works out in a similar fashion. Sorry about that. So with that, we basically find out that for any type of questions for tree recursions, the number of nodes is just going to be let me just erase this part. For any type of tree recursions, the number of nodes that we're going to be getting is going to be a to the power I. So in this case, this is 2 to the power 0, which gives us 1. For this one, for this level, this is going to be 2 to the power 1. That's 2. And this is going to be 2 to the power 2, 4. And the reason why I'm saying this is because we can see another pattern for the row sum. When we have one row, when we only have one node, this thing is then multiplied by the number of nodes, and that will give you the row sum. So 1 times 4n would give you 4n. 2 times 2n would give you 4n. So you don't have to like add all of the nodes separately. You can just multiply the number of nodes of that level times any single node of that level. So that's going to be 2 times 2n. So 2 times 2n is going to give you 4n. Similarly, 4 times n is going to give you 4n. So n plus n plus n plus n is going to be 4n. Right? Okay. So these were some general patterns that we could see. The number of nodes is always going to be a to the power I. The row sum is just going to be any one node of that tree multiplied by a to the power I. So these were the patterns that we found out for number of nodes and for the row sum. Now we're going to generalize this even further. Also, one thing that I forgot to mention was that in this question, the t of 1 is going to be 1. This is the base case, which allows us to basically stop recursing forever and ever. And the next part of this question is going to be, how do I generalize this in such a way that I can figure out what my time complexity is going to be for this function when I hit the base case. So first of all, we need to find out how to generalize my formula of t of n into t of 1. So to do that, I need to know that whenever I'm going to reach my base case, which is going to be at some iteration k, which I don't know what that is going to be, the case, my t is then going to be converted into, and in the same way how we figure out a pattern, we discovered the pattern number of nodes and the row sum. This pattern of a to the power I times any one node will give you this. I can also write it. So a to the power I times any one node would give you the row sum. This thing, this formula and this formula is fixed for every question, but for t of n, this is not going to be fixed. This is something that you have to do on trial and error and based on intuition, and you have to look at the question, and this generalization is going to change for every question. For number of nodes, a to the power I, and for the row sum, a to the power I times any one node is not going to change, but this is going to change. So for this, we can see that for I equals to 0, that is just n divided by 1. For I equals to 1, that's n divided by 2. For I equals to 2, that's n by 4. So the general pattern is going to be n divided by 2 to the power k. Similarly, any one node is going to be over here 4 times, and then just placing the polynomial or the function inside the bracket. So in this case, that's going to be n by 2k. So that is basically the result that we're going to get for any one node. And the number of nodes for this is going to be 2, because a is 2, to the power I, which is k. And the row sum is going to be 2 to the power k times 4 times n divided by 2 to the power k. There you go. It's going to be that. So we can see that 2k is going to cancel out, and we're getting 4n. So we can see that the row sum is constant, which is 4n. Now, how to solve this recursive question? When we're going to reach the base case, that is when we're going to be reaching t of 1, which is 1, this n by 2k, so I'm writing it over here, this n by 2k is going to be converging to 1, and we can write that n is then going to be 2 to the power k, which is then going to be log of base answer k. This k is basically signifying the height of the tree. K is basically the height of the tree. And this k value is always dependent on how you're generalizing this and the inner function of your polynomial. So this is going to be n divided by 2k, and you're going to get log 2n equals to k. Now, there's entire row sum is going to be starting from the iteration I equals to 0, going to my height of the tree, which is log of 2n. And since I don't have any formula for I over here, so we're basically getting 4n, and this 4n basically is a constant. And by the rules of summation, we can also rewrite this by writing I equals to 0 for log 2n and keeping 4n outside 1. And this 1 can be then written as 4n times log 2n. And this is basically the entire row sum that we're going to be getting for the entire tree when we reach the base case. And the time complexity of this, by ignoring the constants, is just going to be O of n log 2n. And if we apply the master's theorem on this question, where a is basically 2, your b is also 2, and your d is 1 because the polynomial value, the degree of polynomial is 1. And for this case, this is just going to be 2 equals 2 to the power 1, which is a equals to b to the power d, gives you n log b to the power d, which gives you n log 2n. Sorry, that's not d, that's n. And indeed, this checks out. So that is how you solve recursive tree questions.